So thank you very much for the introduction and thank you for the invitation. And it's always my pleasure to be in Frankfurt. And so this is, we're gonna report on some work in progress with Claudia Alves and Annika Burmester, who are both in Bielefeld, where Annika is now in Japan, but just for a couple of months. So let me, so first, the B stands for birational. We will come to that a bit later. So let me start with a motivating question is, what is, if I write too small, please just say out loud. So what is the volume, and what I mean by this, let's come to that, of, say, the moduli space of a little curves. Which I'm in the notes. A1. Okay, so one of the motivating questions is about how to think about this volume. So let me approach this in a truly geometric way. So let's consider the space over the complex numbers. Then I can represent the space as a quotient of the complex upper half plane by SO to D, where the group is acting by linear fractional transformations. Right? Here we know that an element in the complex upper half plane will give rise to the complex torus given by the lattice. Okay, so with this point of view, then we can ask, okay, well, let's look at a fundamental domain and calculate the volume of that fundamental domain. So let's do that. So a fundamental domain for this action, maybe you have seen the picture before. Well, here I have my complex upper half plane. So I take my real axis here, imaginary axis here. And so it's given by complex numbers whose imaginary part, so whose absolute value is bigger or equal to 1, and whose real part stands between -1 half and 1 half. So it looks like this. So it's a strip that goes to infinity. So this is going to be a fundamental domain. So maybe I can write this is e to the 6 and e to the 2 half. Okay, so maybe if I think about my volume, in this way I can take the hyperbolic metric on this complex upper half plane and just say, well, the volume of this moduli space is going to be the volume of my fundamental domain with respect to the hyperbolic metric. So, and I can really calculate this, and I'm going to give you. So this is a normalization factor of this measure, and here I take from -1 half to 1 half the real coordinate, and from the unit circle up to infinity, and I integrate my hyperbolic metric. Okay, so I can calculate this, and I'm not going to give you all of the steps, and I can give you the answer. This is always fast, so it's here. So after some steps, you calculate this, and you end up with 1 over 2 pi the second times the theta value, the Riemann theta value at c. Using functional equation, you can write this as minus theta of minus. Okay, so that's a nice nice formula. And so more generally, let's calculate the volume of the moduli space of abelian varieties of genus G. So now I'm gonna so this is usually a stack. So I'm gonna put some level structure to treat it as a variety for later purposes, but actually the volume is doesn't matter. But let's say more generally. So more generally, again over the complex points, I can look at the moduli space of abelian varieties, of principally polarized abelian varieties of dimension G with some level structure. So this is going to be a neat arithmetic subgroup of the symplectic group is P2G. Okay, so I'm doing this to get rid of torsion points of automorphisms. So I can write this again as a quotient of now the Siegel upper half plane modulo this group. Okay, so these are going to be the analog, the higher dimensional analog of the complex upper half plane. So these are some symmetric G by G matrices with positive imaginary. Okay, so now again, I want to calculate the volume in this like differential geometric way. So now we have an analog of the hyperbolic volume or hyperbolic metric now in this space. And so this calculation was done by Siegel in 1943. So calculated this volume. Again, the integral now. I'm sometimes gonna forget my gamma here. And now with the analog of the hyperbolic volume, which now I can view this as, so this like distinguished volume element, I can view it as well as like a differential form. And in this case, the differential form is going to come from the Hodge bundle together with a canonical metric on it. So in this case, I'm going to take the integral over my moduli space and take top wedge product of my Hodge bundle together with the invariant canonical metric on this Hodge bundle. And I take wedge product to the dimension of this moduli space, which is G times G. Okay, so here, so this is the Hodge line bundle. Which is endowed with this canonical invariant metric. Now I can calculate this. Now let me denote this by G, by big G. And Siegel calculated this, and this turns out to be a very nice formula. So here I'm taking the index of my subgroup with respect to the symplectic group. And now I here have a -1 to the G. Here I have a G factorial over 2 to the G -1. And then I have a product of values, of negative values of the Wiener Zeta function. So this is going to be a product up to little g, k equal to 1, theta of 1 minus 2k, and here's 2k minus 1 with a double factorial. So please check if g is equal to 1, and you should recover what was on the board before. So, so this is a very nice formula then involving this negative values of Riemann zeta functions. You can also write down this formula in terms of Bernoulli numbers. But somehow this gave like a relation between some maybe differential geometric volumes with some values of Riemann zeta. Okay, so here we used like this differential geometric kind of volume. And we have seen in the talks maybe also an algebraic geometric way of maybe looking at volumes, right? Last talk we saw the Chow group. So we can talk about a relation between this volume with the algebraic geometric volume, or a top intersection number, a degree, or actually a volume in terms of asymptotic growth of sections. Okay, so the question that I want to put here is, what about the algebraic geometric volume? Okay, so the following is a theorem. A theorem by Mumford, which follows from a theorem by Mumford in the 70s. And so looking at these metrics and a way how these metrics degenerate, he can conclude the following, that actually this volume can be calculated as a top intersection number of an extension of this Hodge bundle to any toroidal compactification of the moduli space of physically polarized. Okay, so he managed to, well, he did not state it in these words, but it is because of his results that you can say that this volume agrees actually with the top intersection number of this extended Hodge bundle, where this is the so-called metric extension of the Hodge bundle to any smooth projective toroidal compactification. Okay, so if you have something in the interior line bundle, this omega on AG, then there are in principle many different ways to extend it to a compactification. By metric extension, this extension is really unique. So you ask the metric to extend in some continuous way with, so you ask it to be continuous except at a codimension 2 locus on the boundary. So these are called Mumford-Gear extensions. So these make this extension actually unique. Okay. By work of Mumford, okay, the metric extends with some mild singularities. These are singularities that are so mild that you actually can compute this using this. So this does not depend on the compactification. So if you read this equality here, where really it does not matter which compactification you take. Okay, the numbers are going to be equal. If you take another compactification, well, the top intersection numbers are going to agree. So this is like a functoriality result with respect to extension of metrics. Okay, so this is nice. But so this talk is then about the following question. Now we have this result for AG, and now we want to try to answer the same question, but for the families, for the universal algebraic. Okay, so the question is, what happens what about, let's first look at the universal elliptic curve. So this is the universal elliptic curve with a level gamma structure. Okay, or of course, more generally, UG. So universal abelian varieties. Okay, so then we have now two things that we have to compute. The first one is, let's look at the differential geometric volume, and then let's look at the algebraic geometric volume, and let's try to compare the two. So again, we have over the complex numbers, we have a nice representation of the universal elliptic curve, or more generally of the universal abelian variety, in terms of a quotient. Okay, so and then we have then again over C, we can represent this space as a quotient. Now I have a semi-direct product. I'm gonna tell you what these are. So now we have a quotient of the Siegel upper half plane times C to the G, and the quotient by a semi-direct product of the same group, giving us the level structure by the so-called Heisenberg group. So this is a subgroup of the full Jacobi group. So we have this nice, so this is then a vibration over this space here, with fibers then given by the abelian varieties. So we can calculate the volume again in this case. This was done by Kai. So Tai in the 80s, yes. So theorem Tai. And we calculated the volume again by looking at the a distinguished volume form. So this is then integral over G of gamma. And now we have a distinguished volume form, which let me call eta. And now this distinguished volume form then also can be calculated in terms of a differential form. But now you take not the Hodge bundle, but you take the analogous on the universal variety, which is called a line bundle of Siegel-Jacobi forms. So this we can calculate now using a top wedge product of the C1 of a line bundle, which is a line bundle of Siegel-Jacobi forms, which again has global sections, some automorphic forms, but we're not going to focus on that, which also comes with an invariant metric. And you take now the wedge product, now 2G plus G, which is the dimension of our universal space. Now this you can calculate, and this turns out to be, well, not that interesting. Well, it's going to be some constant which depends on, so this line bundle depends on two parameters, some weights and some index and some weight, which comes from this automorphic representation. It's going to be a constant depending on M and K. And then we put here some factorial and times the volume of A. So it's basically using a fiber formula. You have then some constant times the volume of the base. So you're not getting anything new. So the hope originally was that you thought that actually you would get some interesting zeta values here. Okay, you thought that maybe you have some zeta values on the base, and by calculating the volume of the universal space, you would get some maybe derivatives of L functions or something. You would get something more interesting, but not. Okay, let's look at the algebraic geometric volume. So now maybe the question is, what about the algebraic geometry form? Okay, so the following. Yes.
Is that using gamma? Does that depend on gamma?
Yes.
So everything is using gamma.
Sorry. This computation.
Yeah. Is it using gamma or is it using?
This one?
Yeah.
No, it's times the volume of AG gamma. Sorry.
Oh.
Yes.
So
You take also the. Yes.
So everything comes with a level and level structure.
Yes, I mean you can do also these calculations you can also do without the gamma, and then you just have index one.
So maybe all the UGs there are UG gamma.
Yes, I'm sorry. I said at some point, and I say it now, I will sometimes forget to write the gamma, but from now on, it's always with the gamma. Yes, the UG here is with the gamma.
And could you say what M and K are?
So this is actually a line model which depends on M and K. So this is a line model which you can see as so we have a vibration from U gamma to A gamma, and then you take then the pullback of the Hodge bundle to the K, and you tensor with the mth power of a B extension line bundle. So here the M and the K. And this comes from a Poincare bundle. So so the M and K and the global sections of this line bundle are going to be some automorphic forms which depend on these two parameters. So one is saying how it behaves with respect to the action of gamma, which is the K, and the other is going to say how it behaves with respect to the action of the sizing group, which is the M. Yes.
Is the data of the M and the K somehow hidden in the neat subgroup? Because the first equation you write seems to be independent of M and K.
I mean, this one depends on the gamma. So you're taking, I mean, of course you're taking automorphic forms with respect to a group action, and the group is gamma, then the direct product has the group.
Okay, but in the
I mean, for any gamma you have M and K.
okay, but if you're in the first equation, you're integrating just this volume form over UG gamma, and that doesn't seem to depend on M or K at all, right?
Yes, of course, because I'm taking the volume form and taking it to be this one, which depends on this.
Ah, okay.
So
That's
this
your
is like
choice of volume
the
form.
distinguished volume form is going to be given by the differential form given by this line bundle, which depends on gamma, K,
Okay.
and M.
Okay,
and,
perfect.
Yes. Okay. So let's look at the algebraic geometric form. So again, we have this notion of metric extensions. We can take, there is also a nice theory of Fourier compactifications of the universal abelian varieties with level structure and without. So you can ask, okay, I take this metric extension to a Fourier compactification. I take top intersection numbers. Is it equal to this? And the answer is no. Otherwise, this talk wouldn't be that interesting. So the following is a theorem which we proved together with Jose Burgos and David Holmes and Robin de Jong. So it says in the same context, it's I take again this L, which again depends on K and M, but I'm not going to write the indices nor the gamma. So we have this lemma, when I take a metric extension over any toroidal compactification, so B, the metric extension to any smooth projective toroidal compactification. Of U gamma, then we have a strict inequality. So the volume that we saw before is going to be strictly smaller than the top intersection number. Oh. Of course, this makes sense to have a degree map, and that this gives you a number. It only makes sense on a compact space. Okay, so you need, in order to have a comparison, you need to go to a compactification. And the hope was maybe that it agrees as it did for the space of abelian, of physically polarized abelian varieties. But no, here it does not. The reason why it does not is because of this metric, how it extends. So in this case, it extends, and the singularities are much worse than in the abelian case. Okay, nevertheless, these objects you can then start to vary over all different compactifications. So you end up with a monotonic net of numbers. Okay, because you have a monotonicity, because this metric comes with some positivity. So you have a monotonicity while you varying through all compactifications. So, and you have a partial order on the compactifications by saying one is bigger than the other one if you have like a map from the top to the other one. So you end up with a poset which is decreasing. So it has to converge, and it converges to this. Okay, so then moreover, we obtain a decreasing net of self-intersection numbers, or of top self-intersection numbers and as you vary over all toroidal. Yes.
Should we think that this is happening because the bigger is the compactification, the worse the singularities of the?
No, they don't get worse. I think one should think of it as the metric extensions are really not factorial. So if you have one compactification and if you have another one there, then the extensions they don't agree on the pullback. But it's not that it's getting worse. It's just that maybe that if you think about the exceptional divisors, it does not stabilize at any point. So you're always adding new exceptional divisors with non-compatible and non-compatible under the pullback. Yeah.
One is comfortable leaving toroidal compactifications to work with like Satake compactifications. Can you make sense of this extension and then say you actually achieve it on the minimal Satake or something?
So in the case of AG, actually you can I mean this works over the Satake compactification. In this case, you can also talk about Satake compactification, but it's going to be the same thing. It's not going to agree. So also not there. And we work with toroidal compactifications because we're going to link it to some combinatorics. And in this case, the singularities are like going to be concentrated only on the like really toroidal boundary or toroidal strata of this toroidal compactification. So it makes sense to read off maybe this errors in a combinatorial way. But with the Satake, it happens exactly the same thing. So, and there was an article which claimed the equality, which was published in ACTA, and it claimed equality using Satake. But they didn't give a proof, and it's wrong. But it does not extend to Satake in an ample way. Okay, so we vary overall, and then the limits, compactification. And in the limit we get the volume of this UG gamma is equal to the limit. And so I'm not going to talk a lot about b-Divisors, nor am I going to give a formal definition, but you can view now this, like this different extensions of this line bundle as a b-Divisor. So a b-Divisor just means it's something that lives on all different modifications and is compatible on the push forward. So this is the same as the top intersection number of a so-called Neff b-Divisor, which comes from considering this whole metric extension. I'm going to denote it BL and the metric because the extensions really depend on the metric. Okay, now the question that is, so this project is about a question about how to actually compute this number. And using some combinatorics. Are there questions?
So you say you want to compute this using combinatorics. Is there an analog for really computing this number with Mumford? Like, so like a big example?
This one?
Yeah.
Well, what do you mean? So in the case of the tie, the formula we got by tie, so that in our baby case, or
Yeah. So the formula you got with like an actual integral and zeta values, like, is it easy to see here with?
yeah, we're gonna we're gonna be a very concrete example. What I mean by combinatorial comparable both parts. Yeah. Okay. So so the strategy is the following. So maybe question is how to compute. How to compute actually this following. So the strategy is the following. We're gonna fix toroidal compactification. So gamma. And now I'm gonna look. So on this compactification, I extend my line bundle in a metric way to this compactification, and then I'm gonna look at the difference. So the difference of this. So let me fix one of these compactifications. So this. Now, before I take intersection numbers. So as I said, you're varying only the boundary. So on the interior, you're always staying the same. So if I look at the difference between this extension at one level and this multiple extension, so this b-Divisor, so BL. So this is really just supported on the boundary. On the boundary of all different toroidal compactifications. Okay, but you're just like changing the toroidal strata of this one compactification that is started with. So I can read off this difference really on the conical complex corresponding to the toroidal compactification that I started with. Okay, so this difference is going to be like a function on this conical complex corresponding to this toroidal compactification that I fixed. So this can be described I'm going to give that complete example in terms of so first it's going to be a homogeneous, positive homogeneous of degree 1 or so-called conical function because it's representing the values, the coefficients along the exceptional divisors. Second, the positivity of the metric gives also some convexity of the function. And I'm going to come back to this in just now. So it's a convex conical function. On the conical polyhedral complex corresponding to the toroidal compactification. Okay, so it is a polyhedral complex. It's an abstract polyhedral complex in the sense that it does not live in a vector space. So first, maybe you can ask yourself, okay, what does convexity mean in a polyhedral space? So convexity, well, it just a priori only makes sense in a convex setting or in a convex set. But so there is, using tropical geometry, there is a way to define convexity of piecewise affine functions using tropical intersection theory, and then you can extend this to the non-necessarily piecewise linear space. Okay, but then this work has already like some tropical positivity inside.
So this convex doesn't mean something complex. This is a secret.
No, because this lives in a polyhedral complex. So it's not on the Siegel upper half plane, it's on the polyhedral complex. So the toroidal complex.
Not left it after.
No, I don't think so. No, I mean the example. I'm gonna give the example maybe of the universal elliptic curve. So and the universal. So let's take this example for. I mean it's convex in the sense that you have a polyhedral complex, and if you so it can be like really like I don't know. And you need that to go from this to this, you need an inequality to hold always. Okay, but let me give you the example. So in the example G equal to 1, then we have, let's take the universal elliptic curve. Let me write it like this with some level structure. So it lives over the modular curve now with some level n. And you can compact, so this is E. So you can compactify, so this is the modular curve. You can compactify this using, so by adding finitely many cusps. And then over each of these cusps, you can compactify the universal elliptic curve by adding over each cusp then one of these n-gons, where n is the same n as here. In this case, for that picture, n is equal to 4. Okay, so that this is a toroidal compactification from the open part to the space. So the conical polyhedral complex corresponding to this toroidal compactification, well, it's for each cusp, you have a two-dimensional conical polyhedral complex, and the two-dimensional cones correspond to this nodes. Okay, so in the local picture, if I have here something like this, so over this node corresponds as smooth two-dimensional cone, which I'm gonna write like this. And in this case, with the data of the invariant metric and this metric extension, then in this over in a surrounding neighborhood of this node, which corresponds then on the conical polyhedral side to a two-dimensional cone, my function, this convex function, is going to look like this. So it's minus xy over x. So, and they glue together when you go from one cone to the other. So on each cone, so being convex in particular means that it's convex on each cone, but you also are asking for some like positivity or some like sign property when you go from one cone to the other. So let's maybe consider this example and let's go to the, in this case, how can we, how does this function serve us to compute this difference? So the reason, like in really purely combinatorial terms, the reason why you cannot compute the volume on any toroidal compactification, that you really have to go to the limit. The combinatorial reason behind this is because this function is not piecewise linear. If it were piecewise linear, then you could just stop at some point. And if you take the compactification that corresponds to the regions of linearity of that piecewise linear function. But since this one will never be piecewise linear on any refinement of this positive quadrant. Okay, so it's never gonna be piecewise linear, hence it's never gonna be, you're never gonna reach the intersection number at the volume at some level. So let's so now how do we, so what this then now we have to take intersections. And so in this case, what are, so the as I said, so this difference that we want to compute, like it's a measure of the lack of how piecewise linear it is.
So may I ask, where are we computing this difference? In what kind of?
So we want to compute the volume.
Yeah.
And we know that the volume is equal to this this limit. So if we can compute at one point the intersection number and the difference, then we can compute the volume. Yeah. So so we want to give a combinatorial interpretation of the correction term. If we have the correction term and we know the intersection at some point at one compactification, then we can also compute the volume. So when we want to compute, we know that this, in this case, this squared is equal to, or let's say, so we know that this volume, we know that the volume of the space of E1 is equal to the limit of this, right? So if we calculate the limit of this, so I want to just take here, calculate the difference of this in terms of this conical of this function. Okay. So if I know how to measure the difference, then using some like algebraic geometric mixed intersection numbers, I can calculate this difference.
So difference means difference of the volumes at a given level.
No, this is a limit.
Yeah, that is the volume, and the other thing is the intersection number, but different means difference of these two numbers.
Exactly.
Yeah.
That's what I want to compute. I want to compute the difference of these two numbers in terms of a combinatorial object. So maybe it's more difficult to compute this combinatorial object. Maybe the most simplest is to compute this directly. But as I said, I motivated the things because we wanted to look for interesting theta values. It turns out that for these numbers, we don't have interesting theta values, but it may be that for the difference we do. And for the case that I'm going to explain now, the difference is actually given by theta value, multiple theta value. And this is what I want to explain now. So somehow my intuition is you're degenerating metrics, and the limit is not in this case like a tropical object, but it's a limit of tropical objects. So how do you compute limits of tropical objects? And the answer here will be, well, some theta functions. So so now maybe I again, so the goal maybe in this case is to compute that we have fixed one extension. So we want to compute this difference using combinatorial form. So again, in the example, we have this nice picture. Okay, we know how this difference in terms of functions. So what is this function actually? This function, you see this different extensions of the line model. Now, array in this two-dimensional cone is going to correspond to an irreducible divisor on some toroidal compactification of UG. Well, the coefficient that you're going to put on this exceptional divisor is going to be exactly the value of this function. Okay, so this is really encoding the coefficients of the newly added exceptional divisors. Okay, so now how do we compute the difference, or how do we use this? So, and the main point is the following: we need to capture how far this function is from being linear. So how do we do that? So there is, let me say here the main result that we use here, or I'm going to state the result and then I'm going to give the explanation. In this case, so for g equals to 1, for the example, in the example we have that this minus this is going to be given by an infinite sum of this Nye function okay. So we're going to get our formula like this by looking really at the difference of how far this function is from being linear. And this is the value of the Mordel's theta function at 2, 2, 2. Mordel's prime theta function at 2, 2, 2. I'm going to maybe give the definition later. So we are interested in formulas like this. Okay. So how the main reason, how do we get this computation? So main or key point is the following very result that you know from school. So if you have this two-dimensional cone and you put here a primitive vector a comma b. I want the greatest common divisor of a and b to be 1. So you know from school, in this case, that there exists unique, so it's like a Euclidean algorithm. There exists unique x and y such that a times x plus b times y is equal to 1 with the property. So we want this relation and we want to pose some some order. So we want the y to be less or equal to 0, and the x to be bigger or equal to 0, and we want to bound by a and b. Okay, why do I want something like this? Because I want to find unique elements here such that this exceptional divisor arises as a blow up of like a unique tower, a unique blow up in a uniquely defined tower of blow ups. So the idea is to find vectors here and unique vectors here and here, such that this one arises as a blow up of the two-dimensional cone besides. Okay, so and then you can put here just so then this cone over here is gonna be let me see. So I guess this is minus y comma x, and then this is gonna be a plus y. Okay, but why? So in a sequence of blow-ups, I want to determine uniquely of whom I have the blow-up in order to compute the intersection, the difference of intersection numbers from the blow-up to the original, to the other one. Okay? So in this case, if I compute this difference, and if I take now here minus, so I want to compute the difference of being linear, so I have to take care of the sign. So what I'm doing is I'm taking phi of a comma b, and this with a minus, plus phi of minus x comma and minus y. Okay, so by convexity, this function is always, I mean, this expression is always going to have the same sign.
So what is phi?
Sorry, the phi is the xy plus on the positive side. Okay, if I calculate this expression, then I end up with something that looks that looks exactly like this. Okay. So up to, I mean, putting some different names, but then you need m and n to be co-prime, and then you end up with something like this. And then you're gonna, so this is like the error term. If I take, so times the top intersection number of the exponential divisor, which is -1, then what you're doing is you're adding, the correction terms is gonna be by adding all of these terms squared times the top intersection of the exponential times -1. And you have to do this for, so this is the error term corresponding to this one ray. This is the thing that you have to add while taking the difference. But for each ray, and for each ray you have to do, you have to take away this error term. So at the end, what you're doing is you're summing over all primitive numbers and putting the coefficient of the top intersection number of the exponential divisor. So you're adding over all of these with a minus. Okay?
Can I ask 2 questions?
Yes.
The one that's A and B in this example, like you started with AB, so it's 1 over AB times A plus B.
Well, the thing is, this is just a function on the, so I put here variables x and y, but I mean so I should
below.
here.
Yeah.
Yeah, no, these are, yeah, some,
So like
A
does that
plus
correspond
something-
to A and B, or
it depends on
corresponds
A, B, x, and y. But these are related by this formula.
to-
It's just a
why
way
is
to
it
represent
squared
again the
in the
co-prime elements, sorry?
Why is it squared in the formula?
Because you're taking like squared, like you're taking intersection number in a two-dimensional expression. But at the end, I mean, this is just so that the fact that you can calculate this very explicitly from this picture, and that you know the correction term along any of these rays, boils down to the fact that you can find of whom I am the blow-up and calculate the difference of the intersection numbers of that with the blow-up. Okay, if you can do this for all of them and in higher dimensions, then you can calculate the difference. So in this case, this gives us this nice formula. So I'm gonna rush a bit. We have one theorem, and I'm gonna. I mean, actually, I want to talk also about our main difficulty. So actually, in dimension 2, then with Claudia and Annika, we can compute the difference of one of these toroidal left b-Divisors for the top intersection number with any fixed top intersection number of and any fixed compactification as a value of one of these conical Zeta functions. So I'm going to write down the result. And then I'm going to point out some, well, the main difficulties to extend it to higher dimensions. So the theorem is, this is in general, we're not taking universal Abelian things, but it is like general for any smooth projective toroidal classification. Now we have to fix dimension 2 and assume that a line model L, so L is a line model on X and on U extends to an F. An F is like a positivity notion, which is well behaved for these b-Divisors. L. So as we vary over all compactifications. And again, if we have a setting like this, then the difference again is going to correspond always to one of these convex conical functions on the conical polyhedral complex corresponding to the toroidal compactification. So we can let L or this phi, this difference. So this is going to be a convex function. On this conical polyhedral complex corresponding to the compactification, and then the result is then that you can compute the difference of intersections as a value. And now, so this Mordell-Tornheim functions, these are a special class of so-called conical Zeta functions. So this is going to be a conical Zeta function. So the Zeta function, the conical Zeta functions are going to start by summing up over and counting, or taking sums over all interior lattice points of a given cone. I'm not going to have time to explain this, but so you can attach to this function here one of these cones, and then so this is going to be a cone inside a a vector space, maybe of dimension higher, but you can then write then this difference as a conical zeta value evaluated in 2, so in 2 and a vector 2 depending on the dimension. So as a particular example, you can realize the Kornheim zeta function as one of these conical zeta functions. And maybe I want to say that, so this conical zeta functions, you know about, so these are also extensions of multiple zeta functions. And multiple zeta functions are interesting because they arise a lot in mathematical physics. Okay, so these can also be seen as values of these multiple polylogarithms, which arise by calculating things that are represented by Feynman integrals, like that represent behavior and interaction of subatomic particles. So there is a very main conjecture in this field, which is about computing all algebraic relations of multiple zeta functions. Now, a strategy that has been started in a couple of years ago was, okay, to embed multiple zeta functions in the world of conical zeta functions. And the world of conical zeta functions is nice because it has some combinatorics. Like there are 2 main relations, algebraic relations between these multiple zeta functions, which are the shuffle and Stoffel products. You can see, and the conjecture is that these are the 2 only relations that are there. So the strategy to embed this in this space is because this Stoffel and shuffle can be interpreted combinatorially in terms of cones, cone open and closed cone subdivisions. Okay, so maybe here, so if you can classify multiple zeta values inside here, and you can control more these algebraic relations inside this conical zeta value space, then it's a way to approach the conjecture. Okay, maybe the last thing I want to say is the difficulty, and then what we're trying now, and maybe if you want to talk or are interested in this later, is to extend exactly this result, which was from school, to the higher dimension case. Okay, so what does that mean? You start with some barycentric subdivision, say in dimension 3. Yeah, so in dimension 3, you have, and there is a very a nice tree structure giving you this. So you start, in this case, you start by some basis vectors. Okay, you start there. So this say, and you take then first barycentric subdivision, 1, 1, 1. So this is going to be, say, generation 1. So this is generation 1. So G maybe not generation. And now, as you know, if you take for dimensions bigger or equal to 3, well, you don't only have blow-ups at points, you also have to control blow-ups at curves and in higher dimensions more. So what we're having here is you're going to start subdividing. You're taking blow-ups at 2-dimensional or 3-dimensional things or at points. We're also taking blow-ups at curves. You're going to stop taking here, subdividing 3 times here, and also in these parts. So these are going to be generation 2. Then you start generation 3 and generation 4. You have concrete numbers of how many elements arrive of degree 2 or of degree 3. But the question is, given any primitive vector, so in this case of length 3, but you can do this in any dimension. I give you any one of these sequence of 3 numbers that are co-prime. So the biggest common multiple is 1 of the 2. And I ask you, in this algorithm, does this come from a blow-up of a point? Or does this come from a blow-up of a curve? And can you give me explicit equations for the parents or from the vectors that are giving this as a blow-up in this algorithm? Okay, so in the 2-dimensional cases, it's very simple, and it boils down to this Euclidean algorithm. Here, we don't know how to do that. And somehow, it seems to be it it should, I don't know, I mean, maybe it's more difficult, but it seems like there should be like a arithmetic, like, reason of this generation and degree of such a sequence. But I'm gonna stop there. I'm gonna thank you for your